Alright, so welcome to a new topic. In this topic, we're going to begin by discussing work. And work is going to lead to a change in energy. And as we progress through this topic, we're going to talk more and more about energy. However, energy is probably one of our first most abstract terms, where it's a term and a quantity that allows us to place constraints on the system, according to the laws of physics. But at the same time, it's more of an accounting term where we have so much energy, and that having so much energy leads to how the system's velocity or position changes from point A to point B. This is a little bit more nebulous than when we talk about velocity and acceleration. So those have very concrete definitions, where energy is something you have, and it's going to get changed into another type of energy, which is going to affect how the object behaves. So before we get to energy, though, let's talk about work, because there's another half of this equation where we're saying work leads to a change in energy. So energy final minus energy initial. But in order to then change that energy, we have to do something to the system. And that's going to lead back to what we just talked about in topic 4. So work occurs when a net force, so the same net force in the x or net force in the y that we discussed in the previous topic, is applied to an object over a certain displacement. So now instead of dealing with things occurring in terms of time, now we're dealing with things occurring in terms of displacement. Now there is one caveat to this. In order for work to occur, the force must be parallel to the displacement. So this means that in order for work to occur, force net in the x goes with displacement in the x. Force net in the y goes with displacement in the y. As you see in the relationship I've written down here, it's an or. Force net in the x times delta x, or force net in the y times delta y. And these relationships work best whenever you have one quantity that is solely in one direction. So if you're displacing only in the x, it's best to establish what your force net in the x is and just multiply by that displacement. Since this is a calc-based physics class and we discussed dot products, you can also take the force vector dotted with the displacement vector. We're using s because this quantity may be curved. So you're going to have a function that describes both the x and y path together. So you're going to have a vector that has an x, a y, and potentially a z term to it. So you can do the dot product, because remember the dot product of a dot b gives you a times the magnitude of b that's in the same direction or parallel to a. So in essence, this statement here gives you the same thing as up here, where you're going to only end up multiplying your x components with your x components and your y components with your y components. Because remember, the expanded form of this would be this. So you're multiplying your x together and your y's together. This is a little bit of a weird concept to us, the fact that you could be applying a force, but because it's not parallel to the displacement, you aren't actually doing any work. Because we tend to associate work more with chemical energy rather than mechanical energy. So you think about like a bodybuilder holding a really big dumbbell, and the person's sweating and they're straining. So they might be doing some sort of using energy chemically in their body in order to hold that position, but they're not doing mechanical work. Mechanical work requires motion. And so until they lift that dumbbell straight up against the force due to gravity, they are not doing any work. Because then, since you're lifting straight up and applying a force in the y direction, then you're displacing and have a force parallel to each other, and that's when work is actually done. So be careful to not equate work as a term we use in everyday life and mechanical work, which we're talking about here in a physics course. Now, work is a scalar quantity, so remember the results of a dot product are a scalar quantity. However, it can be positive or negative, because remember, work leads to a change in energy. So you can have a positive change, where the final is greater than the initial, or you can have a negative change where the final is less than the initial. So it's whether you're adding or removing energy from the system when the work is done. This allows us also, we're going to have a new unit. So we're multiplying force times displacement here. So we're going to have a Newton times a meter, which we can expand the Newton into a kilogram meter per second squared. We still have a meter we're multiplying by, so that becomes a kilogram meter squared per second squared. And we're going to call a kilogram meter squared per second squared a joule, represented by a capital J. Now, the work we've been discussing so far is due to a force that is constant. So the whole way through the motion, the force is going to have the same value. But what happens if it doesn't? Now, I have two force versus displacements displayed here. One, the force is constant, so notice it's a horizontal line, so the force is staying at the same value the whole way through the motion. And one where the force is increasing literally with the displacement. So it is not a constant value. So the force here is different than the force applied here. Now, we talked earlier that whenever we have something that is multiplied, so we're multiplying force times displacement, we can use the area underneath the curve of that graph in order to find the value. So we did this whenever we were looking for velocity and we had an acceleration versus time graph. So we're going to do this here where we can find work from using the area underneath of a force versus displacement graph. Now, if we look at our graph here on the left, this assumes constant force. So this is the situation we were dealing with earlier in the video where the force stays the same value the whole way through the motion. So you can pick the force value at any point along that and use that because it's just the same value. And so you end up with a relationship that is the same as the one we had on the previous page, where work equals length times width, because we're dealing with a rectangle here. So it's going to equal force, and you would use your initial position and your final position, so your delta D. But if we go over to our second graph, for our second graph, we would have to be given some sort of function to describe this graph. So this is a linear relationship where the force in terms of position is some constant, which would be the slope, x to the first power. So that type of relationship for a force gives you the linear relationship we're describing in this graph here. And there's always this instinct to plug in to something like this, where you take the force or the position at the final position, plug it in here, and do work equals force times the change in displacement, and you'll use this value and this value for the change in displacement. But the problem is that then assumes that the force is that value the entire time, but you can see that it's not, because the force is this value when you're at this position, it's this value when you're at this position, this value when you're at this position, etc., etc. So you have to take into account the fact that all this work here is not done. So it's not a rectangle, it's a triangle. So let's get rid of all of that, because that's not right. And let's talk about what we actually need to do. So graphically, if we have a shape something like this one's not too bad to do just graphically. So you can do work equals 1/2 base times height, which is going to equal 1/2 times your constant, because that's your times x2 minus your constant x1, because that's what your force is equal to up here, times then x2 minus x1, because then you're multiplying by, so you're taking base times height, where your base is your displacement, and then your height is your force. But if you have something that's a little more complicated where you can't just use an area formula, or you're just given the function and not the graph, the area underneath the curve is the same thing as taking the integral. So I could plug this function in here for f of x and integrate in terms of x. And that would give me a relationship for this example that looks like this, but you could do this for any sort of force function that I give you, that when you plot it out, you might not get a standard shape that you can figure out the area underneath the curve. So whenever the work is due to a non-constant force, in order to establish what the work is, you need to integrate in terms of x, or else, as I pointed out up here, you end up including work that wasn't actually done by assuming the force is constant the whole way through the motion. The other thing I'm going to point out in conjunction with this is that whenever you have a non-constant force, this means that the acceleration in turn is not constant, because remember that force is equal to mass times acceleration. So if you take your force function and divide by mass, you get your acceleration. So since your force is in terms of x, that means your acceleration would be in terms of x as well, and so it would change with position. And I point this out because occasionally there are problems that are intended to be solved with a technique I'm going to introduce in the next section that students go back and try to use the kinematic equations to solve. But the kinematic equations, remember, assume that acceleration is the same value the whole way through the motion. And so the acceleration you get from a non-constant force cannot be plugged into an equation that assumes that the acceleration is constant.